Hello researcher lovable, welcome to Material Research Review. Today we are going to see 2D material application part 2, and the title is the highly defective understanding the role of graphene structure for the stable lithium metal plating. This article published in Advanced Energy Material recently. Professor Liu, the Institute of New Energy and Low Carbon Technology, Sichuan University in China. What is the highlight of this work? Actually, in lithium ion battery or lithium metal battery, it will grow irregular dendrimic on the surface. So that is one of big drawback for literatures for application point of view. And the lithium dendritic as leading the short cycle life, and potentially safety concern also one of the big drawback of the lithium ion battery and lithium metal battery. So here, without the free dendritic, experimentally they proved from here this literature. The author synthesized defect-free graphene. That material can help to the dendritic-free surface on the lithium metal surface. So this is the highlight of this paper. And after how they synthesize the defect-free graphene, they designing experimental setup like flow-aid sonicated exfoliation method. They lab itself they designing the experimental setup. Once the NMP and the graphite flakes both mixed and continuously flowing, and sonicated both simultaneously did. So after they getting defect free graphite, from that defect free graphene ink they coated with the graphene modified copper surface. After the lithiation, the stable solid electrode is a solid electrolytic interface. After the stabilized with the lithium metal anode for anode electrode. Here, this experimental condition, previously also they used the carbon nanotube. Lithium foil is the substrate. On the surface they coated with the carbon nanotube. Same the lithium metal batteries, they publish in Nature Communication. Maybe this paper only they inspire with, they prepared with defective graphene, because the paper 2018 they publish in Nature Communication some other group. And so that paper only they inspired, and maybe it will did this free defect free graphene to lithium metal batteries. After that, how they the synthesis material of the characterization did here the AFM they did. The comparison purpose, reduced graphene oxide also they synthesized using the Hammers method. Uh, uh, the AFM image showing the defect free graphene is around the height plot is showing 1.5 nanometer. That one you can see the image, and they compare with the graphene reduced graphene oxide. It's so around 12 to 12 nanometer, 12 nanometers showing the height plot. They compared the TM image both here, and the diffraction pattern also they did uh, from the diffraction pattern they plotted with one line, so that line the intensity also they kept in inside the picker. um, they compare with reduced graphene oxide also. You can see the 100 and 110 is showing the pattern. The IMAG also they did. Here the IMAG is built clearly showing the that graphene pore, but in the case of reduced graphene oxide not clearly showing. After that they compared with the XPS for Raman, XPS and Raman they compared both material like free defect free graphene and reduced graphene oxide. Here you can see the defect free graphene almost 98% for carbon, and 1.3% it only oxygen showing for defect free graphene. And reduced graphene oxide the carbon showing 90% and oxygen showing 8.1% and nitrogen sulfur showing 1%. After that and they compared with the Raman plot in the defect free graphene, the intensity ratio of D band and D band divided by G band is equal to 0.707 they got. This is called like a multiple layer. And after that they with reduced graphene oxide, that D band G band intensity ratio 0.89 came. After that they jump into application part. Used the electrolyte like ethylene carbonate and ethyl methyl carbonate and diethyl carbonate electrolyte solution they used. After that they compared with uh, the both they compared graphene defect free graphene and reduced graphene oxide, and some control experiment only the copper foil they did. And here two they compared with the first cycle charge and discharge behavior of graphene defect free graphene and reduced graphene oxide. You can see the plot almost the charge cycle started with the high voltage 3 volt to 0.01 volt up to, and after discharge first cycle discharge also, and they compared both the difference is showing 148 microampere hour per gram. They compare with reduced graphene oxide also, that one showing 1863 microampere per hour gram. After that one plot the steady state cycling behavior also they compared with both. Compare then graphene oxide the defective graphene are more stable and high up to high voltage also it will stable, so that plot they showed. After that the comparison with the coulombic efficient for the both material. Here they observed coulombic efficiency almost 78% for the defective free graphene. In the case of reduced graphene only the 3.5 uh, uh, 35.4%. It means the twofold increasing the defect free graphene. After that they compare with the electrochemical impedance analysis Nyquist plot of both material. Here graph defect free graphene showing very stable, and reduced graphene doesn't show very clear, and stability also very less compared than defect free graphene. Electrochemical impedance analysis, first cycle, 100 cycle, they both compare. Here they used the two material plus additional control experiment for the bare copper one. And here you can see the plot, the defect free graphene showing initial cycle good impedance, and 100 cycle also very good impedance. But in the case of reduced graphene oxide, initially first cycle active more, and after the cycle 10th cycle it will decrease the impedance, and bare copper also doesn't showing. Here they compared with one table, first cycle, 100 cycle, that one charge transfer resistant is high for the defected graphene first cycle. Comparison 100 cycle, 100 cycles also it will increase the charge transfer resistant and surface film impedance also increasing for the defect free graphene compare than reduced graphene and if, first cycle and 100 cycle. In the case of bare, it's showing some impedance for initial cycle, but under cycle unstable, the circuit is shorted, they saying. So this is the one good evidence for the comparison purpose, the table they make here. First lithium metal nucleation potential they compared with the three bare copper and reduced graphene oxide and defect free graphene. Here initially and the defect free graphene doesn't so good because after the cycle increase, and only it will the highly stable. After that over potential they compared with the three catalysts. The here also the graphene oxide only showing the initially up to the 10 cycle plotted. Here the graphene oxide only showing more because the graphene oxide initially more active, after that the impedance is decreasing. So after 20 cycle the graphene oxide and copper bare copper over potential become unstable. So that only this plot showing. After the plating stripping coulomb efficiency different current, here you can see the comparison on the two catalysts. The defect free is the highly stable, and stay the cooling efficiency also 90% they got. And after that different current voltage, uh, 0.5 to 4 microampere per centimeter square they applied. So here also it will more stable only they observe compared than other catalyst. And one more, the after under cycle the electrode surface is fully platted condition. They took SEM. Here they said lithium metal surface is defected free graphene is showing highly stable and under electrolytic. In the case of reduced graphene oxide, stable but not that much stable. In the case of bare copper, non-stable, it will tend to make the growing on the surface of lithium metal. So one of the best evidence for this paper to free and tenderic lithium metal surface in battery. So overall this work is first demonstrated for the that lithium free dendrite formation on the lithium surface. So that one help to defect free graphene is helping to stop that growth. This one really very novel work only, but I observed some drawback of this, where they synthesize the characterization itself. Some drawback I observed. They said this one, and Raman peak also it will showing like a multiple layer. How they got IMAG image like a well clear pore graphene, I don't know. And the AFM also it will show 1.5 nanometer thickness and thickness. So this one cannot possible to take. IMAG also cannot see the that graphene pore. And the defect free graphene material, the unclear evidence for the defect, but only they showing that diffraction pattern only. This is the diffraction pattern intensity they compared. This is called like a free graphene, they said. This is the one drawback only, but not very clearly proved for defect. And also they compared with reduced graphene oxide. Why not they used defect free graphene they used, and they compare means without defect with defect, both they compare means that one very good comparison. Why both different they compare, we don't know. This is the major drawback. All these things they corrected means this one like nature material work only. Application point of view, this is the very good. One plot they compared with all graphene, reduced graphene oxide is more active compared than defect free graphene up to 10 cycle. So if people this type of data cannot give what they synthesize, that material only they will show best. In this paper after 10 cycle only it will grow, the stability is increasing, like that they said. This is one good future possibility work. They reported defective free graph in 2D material. Why not use the other 2D material like molybdenum sulfide or tungsten sulfide, other 2D material also. That also it possible to deleting the dendritic growth on the lithium metal surface. And another 3D material also they reported in the same application previously. Several letters are also there. One of the the 3D material synthesis using the nickel foam is the one of the best material for 3D structure. Thank you for your kind attention to watching this video. Welcome to your valuable command. Thank you.